Welcome to another episode of My Weird Prompts, an AI-generated podcast featuring the random prompts of Daniel Rosehill as answered by a revolving cast of friendly AI characters. Join us for deep dives into AI, technology, and whatever other random thing Daniel finds fascinating today. Subscribe on Spotify or your favorite podcatcher. Now, today's episode.
This episode was generated using artificial intelligence. Please verify facts.
Hey, Herman and Corn. So I picked up a Raspberry Pi about 4 years ago, the first one that I bought. Didn't do much of this until a few months ago, I would say, maybe a bit longer, and was looking for a way to drive a little display, an alarm panel, which we should do an episode about DIY alarm systems, although I thought we had done one. Maybe I just haven't listened to it yet. But I'm using Alarmo and Home Assistant and sensors, and I needed to set up a control panel. So my initial instinct was to use Android, and it took me a while to wrap my head around the idea that you can actually get better value for money and better performance just with this really, really tiny computer, these single circuit boards or SBC computers. So the Raspberry Pi worked nicely, and it's proven to be kind of versatile, and you can do a lot with it, or pretty much anything with it almost. And then I wanted to find, with little Ezra, our delightful new arrival, I wanted to find a way to have not really multi-room audio, but being able to play a podcast in different rooms. So I saw that the proper networked speakers were super expensive, and it was actually a thrifty move to find some old USB speakers and just connect them to an Orange Pi, which, for those who haven't ventured beyond the Raspberry Pi part of the SBC ecosystem, there's loads of different types now and different distros ranging from Raspberry Pi OS through to Armbian, Debian, Ubuntu, you name it. So that worked actually pretty well, and it's kind of got me thinking how powerful it is, or how to just install the bare bones of a computer, it can actually fit in your pocket. So I've had these up and running, and they're doing a great job. And just out of the box, they come with like the fundamentals, like HDMI out, USB in. You've got Bluetooth, Wi-Fi generally, so networking, a tiny processor, and the ability to drive a display. So just was that served my networked speaker use case just fine. But I noticed that they have these GPIO headers, and that this is kind of the interface where people take it further, and they allow you to connect an awful lot of stuff to it. Now, I haven't done much in the custom hardware area like ESP32, although I've always wanted to explore it. And I always had the idea that you needed like custom something, like a something between the computer and the board in order to, I don't know, program, work with these things. And if I'm not mistaken, you can just use USB. Firstly, that's my first question. Is that correct? And question number two, as I'm using this mostly for Home Assistant, what are some projects that people can do in order to actually use these GPIO headers? What are some things you can connect to it? But before we get too far into that part of it, I'd love to just understand at a more fundamental level, so I know that I'm grasping the hardware right. As I mentioned, I've done computer builds and stuff like that, but that's kind of the more or less the extent of my hardware experience, which is quite different. It's taking components that other people have built and connecting it in a fairly straightforward manner. So the whole enterprise of taking printed circuit boards and connecting your own components is, I think, the next step, and something I haven't really done before. So I'm just wondering exactly how that works. Where do you get started? And is it kind of already a sort of breadboard system, by which I mean you don't have to do any soldering, you can just connect what it needs? And finally, Herman and Corn, sorry to stuff in so many questions, I'm beginning to come across the term pinout a lot. You see pinout diagrams. Explain exactly what a pinout is, and I presume that if I'm picking up a board and and trying to find what I could add to it. Knowing the voltages and the pinout is probably one of the first things I want to be doing. Herman and Corn, I'd love to learn a bit more about what you can do. What are those GPIO headers for? And how can you extend a Raspberry Pi or another SBC, especially in the context of home automation?
Hey everyone, welcome back to my weird prompts. It is Monday, February 16th, 2026, and I'm your host, Corn. Today we are diving deep into the fascinating and sometimes intimidating world of tiny computers and custom hardware. It seems like our housemate Daniel has been spending an incredible amount of time in the workshop lately. He has been tinkering with some pretty ambitious home automation stuff. Things like custom alarm panels and multi-room audio setups using Raspberry Pis and Orange Pis.
Herman Popplebear here, and I have to say, I absolutely love where Daniel is going with this. It is that classic, beautiful journey we see so often in the maker community. You start as a software person or maybe a PC builder, and then suddenly you have this epiphany. You realize you can actually control the physical world with code. It is a massive leap in perspective. Once you make it, your house never looks the same again. You stop seeing a door as just a piece of wood on hinges. You start seeing it as a potential binary data point. You see a light switch not as a manual toggle, but as a node in a distributed network.
It is a really interesting transition because Daniel mentioned he is already comfortable with standard PC builds. That is a fantastic foundation. Knowing how to seat RAM and plug in a GPU is great, but single board computers, or SBCs, are a completely different beast. When you build a PC, you are mostly plugging finished, polished components into standardized, keyed slots. It is almost like high-stakes Lego. But with a Raspberry Pi 5 or an Orange Pi 5 Plus, you are often working much closer to the metal. Daniel was asking a really fundamental question. Can he just use USB for everything? Or does he need a special interface? And specifically, what are those 40 metal pins, the GPIO headers, actually for?
That is the perfect place to start the conversation. In the traditional PC world, USB is the undisputed king. You want a mouse? USB. You want a high-definition camera or an external drive? USB. And for Daniel's multi-room audio project, using USB speakers with an Orange Pi is actually a very smart, pragmatic move. It is simple, the drivers are almost always already baked into the Linux kernel, and you get decent sound without much fuss. But we have to remember that USB is a high-level, complex protocol. It is designed for massive data transfer and sophisticated device negotiation. If you just want to know if a door is open or closed, or if you want to blink a single tiny LED to show the system status, USB is massive, unnecessary overkill. It is like using a semi-truck to deliver a single postcard. That is exactly where the GPIO headers come in.
GPIO stands for General Purpose Input-Output, right? I have seen those rows of metal pins sticking out of the boards. To a beginner, they look a bit scary. Like something you might accidentally break, or worse, short out and kill your expensive board.
They can be intimidating, but they are also the most powerful and liberating part of the board. Think of them as the direct nervous system of the computer. Unlike a USB port, which has a very specific physical shape and a rigid set of rules for how it talks to the world, a GPIO pin is a blank slate. It is pure potential. In your code, you can tell a specific pin, hey, you are now an output. When I give the command, I want you to send out 3.3 volts of electricity, or you can tell another pin, you are an input. I want you to watch this line and tell me the exact millisecond you see voltage coming in. That raw simplicity is what makes them so incredibly versatile for home automation.
So if Daniel wants to build that alarm panel he mentioned, he wouldn't use USB for the door sensors.
Exactly, he definitely shouldn't. A door sensor is usually just a simple magnetic reed switch. When the magnet on the door is near the switch on the frame, the circuit is closed. When the door opens and the magnet moves away, the circuit breaks. You don't need a whole USB controller and a complex software stack for that. You just connect one side of that switch to a ground pin and the other side to a GPIO pin configured as an input. You can even use what we call a pull-up resistor, which is often built right into the chip to keep the signal steady. The computer just watches that one pin. Is it high or is it low? If it changes, the door moved. It is instantaneous, it uses almost zero processing power, and it is incredibly reliable.
That makes a lot of sense. It is about using the right tool for the job. But let's talk about the physical connection part. Daniel was asking about how to get started without necessarily diving into a world of soldering irons and permanent modifications right away. He mentioned breadboards. For someone who has only ever swapped out a video card, what does that actually look like?
Breadboards are the absolute best friend of the hardware curious. If you haven't seen one, it is a rectangular plastic block filled with a grid of tiny holes. Inside that plastic, there are hidden metal clips arranged in a very specific pattern. Usually, the long rows on the outer edges are connected horizontally. We call those the power rails. The shorter rows in the middle are connected vertically. The beauty of it is that you don't need a single drop of solder. You just take a jumper wire, often called a DuPont wire, which is a little wire with a plastic-coated metal tip, and you poke it into a hole. It is exactly like building with electronic Legos. You can prototype an entire alarm system on your desk in 20 minutes.
So for Daniel's alarm panel, he could have his Orange Pi sitting there, run some jumper wires from those GPIO pins to a breadboard, and then plug his sensors or status LEDs into that breadboard to test the logic before he ever touches a mounting bracket.
Precisely. It allows for rapid, consequence-free prototyping. If you realize you plugged a sensor into the wrong pin, or you want to try a different resistor value for an LED, you just pull it out and move it. No harm done. Now, for a permanent installation like an alarm panel that is going to live on a wall in your hallway for the next 5 years, you eventually want to move to something more solid. You might move to a perma-proto board which has the same layout as a breadboard but requires soldering, or even design a custom-printed circuit board, a PCB. But for learning, and for the version 1 of any project, the breadboard is where the magic happens. It is where you find out if your idea actually works in the real world.
You mentioned something earlier that I want to circle back to, because Daniel asked about it specifically. The pinout. I have seen those diagrams online with all the different colored labels for the 40 pins. Why is that so critical? And why can't I just plug things in wherever they fit?
The pinout is your map, your manual, and your insurance policy all rolled into one. If you look at a Raspberry Pi 5 or an Orange Pi 5, you see those 40 pins. To the naked eye, they all look identical, but they are very much not. If you accidentally connect a 5-volt power pin to a data pin that is only designed for 3.3 volts, you can literally fry the processor in a fraction of a second. We call that letting the magic smoke out, and once the smoke is out, you can't put it back in. The board is dead. The pinout tells you exactly which pins are for power, usually 5 volts or 3.3 volts, which ones are ground, and which ones are the general purpose pins you can safely control with your Python or C++ code.
It is not just about power and ground, though. Some of those pins have special labels, right? I have seen things like I2C and SPI.
Great catch, Corn. This is where it gets really exciting for advanced home automation. While most pins are general purpose, some of them are hardwired to speak specific digital languages. You will see labels like I2C, which stands for Inter-Integrated Circuit, or SPI, the Serial Peripheral Interface, or even UART for serial communication. These are protocols that allow the Pi to talk to more complex components. For example, if Daniel wants to add a tiny OLED screen to his alarm panel to show the current weather or the system's arm status, that screen probably uses I2C. Instead of just being on or off, the Pi sends a sophisticated stream of data over just 2 wires to tell the screen exactly which pixels to turn on.
So the pinout tells you which specific pins on your board are capable of that I2C communication? You can't just use any 2 pins.
Exactly. On a standard 40-pin header, pin 3 and pin 5 are almost always the I2C data and clock lines. You have to use those specific ones if you want to take advantage of the built-in hardware controllers on the chip. If you just pick 2 random pins, you would have to write a lot of incredibly complex code to manually simulate that language, a process we call bit banging, and it is much slower, less reliable, and a total headache. The pinout is what allows you to use the board's native intelligence.
Okay, so we have the hardware side covered. We have the breadboard, the jumper wires, and the pinout map. What about the software? Daniel mentioned he is using Home Assistant and something called Alarmo. How do those GPIO pins actually talk to the automation software?
That is the beauty of the ecosystem in 2026. If he is running Home Assistant directly on the Pi, there are built-in integrations that can monitor the GPIO pins directly. But what a lot of power users are doing now, and what I would strongly recommend for a multi-room setup, is using something called ESP Home. Even though Daniel is using Raspberry Pis and Orange Pis, which are full-blown computers, he might find that for simple sensor nodes in every room, he can use even smaller, cheaper microcontrollers like the ESP32. But since he already has the SBCs in place, he can run a small script, often in Python, that watches the pins and sends a message over the network using a protocol called MQTT to Home Assistant. Home Assistant then sees that message and says, "Oh, the front door pin just went high, I should trigger the alarmo sequence."
It sounds like the SBCs are acting like a hub for all these smaller physical interactions.
They are. And because they are full Linux machines, they can do so much more than a simple microcontroller. Daniel could have his Orange Pi 5 playing high-quality music via USB speakers while simultaneously running a beautiful touchscreen alarm dashboard via HDMI and monitoring 10 different door and window sensors via the GPIO pins. It is a massive amount of multitasking that a smaller chip just couldn't handle. The Orange Pi 5, in particular, has an 8-core processor that is absolute overkill for a door sensor, but it means the system will never lag, which is exactly what you want for a security system.
I want to talk about some specific projects for the GPIO headers that would fit Daniel's home automation theme. We talked about door sensors. What else could he do to make his house feel smarter?
One of my absolute favorites is the physical status LED. It sounds simple, but having a physical light on the wall that turns solid red if the alarm is armed, or pulses blue if the laundry is done, is so much more satisfying and effective than a notification on your phone that you might miss. You just connect an LED and a small resistor to a GPIO pin. Another big one is relays.
Relays are for controlling things that use a lot more power, right? Like actual house lights or motors.
Exactly. This is a crucial safety point. A GPIO pin only puts out a tiny amount of current at 3.3 volts. You cannot, I repeat, cannot plug a desk lamp or a heater directly into a Raspberry Pi pin. Well, you can, but only once, and then you will be buying a new Pi and possibly a new desk. A relay is an electrically operated switch. The Pi sends a tiny, safe signal to the relay, which then clicks a physical metal contact into place to turn on a much larger circuit, like a 110-volt light bulb or a garage door opener.
That sounds like a great way to bridge the gap between the digital world of the Pi and the high-voltage world of a house. But I imagine there are some serious safety concerns there.
Huge safety concerns. If you are working with mains electricity, you have to be incredibly careful. For a beginner like Daniel, I always recommend starting with pre-built relay modules that have built-in opto-isolation. This uses light to bridge the gap between the Pi and the high voltage, keeping them electrically separated. It keeps the high voltage far away from your expensive Orange Pi. There are also great smart plugs you can buy that are already safe and enclosed, but for something like a custom alarm panel, a small relay module inside the box to trigger a physical siren is a classic, rewarding GPIO project.
What about environmental sensors? Daniel mentioned multi-room audio, so maybe he wants to track the temperature or humidity in each of those rooms too.
Oh, absolutely. Sensors like the BME280 are fantastic for this. They are tiny, they cost a few dollars, and they use that I2C protocol we talked about to give you very accurate temperature, humidity, and even barometric pressure readings. You can also find air quality sensors for CO2 or light sensors to detect if it is day or night. One of the coolest things right now in 2026 is MEM wave presence detection. Unlike a standard motion sensor that only sees you if you are moving, an MEM wave sensor can detect the tiny movements of your chest as you breathe. You can use a GPIO pin to connect one of these, and your multi-room audio system could automatically follow you from room to room, or turn off the music only when it is absolutely sure the room is empty.
That is a very cool, futuristic idea. It really shows how adding just a few dollars worth of sensors to those GPIO pins can make the whole system feel more intelligent and responsive.
It really does, and I think that is the aha moment for most people. When you realize that you aren't limited to what a manufacturer like Nest or Ring thought you wanted to do, you can customize the hardware to fit your specific life. Daniel's house is different from ours, and his needs for an alarm system are unique. The GPIO header is the gateway to making the technology serve him rather than him adapting his life to the technology.
So, for someone like Daniel who's just starting out with this custom hardware side, what is the very first thing he should buy after he has the board?
A comprehensive starter kit. You can find them on sites like Adafruit or Pimaroni for $20 or $30. They usually come with a high-quality breadboard, a big bundle of jumper wires, a set of various resistors, some LEDs in different colors, a few tactile buttons, and maybe a couple of basic sensors like a light-dependent resistor or a temperature sensor. Having that variety on hand is crucial because it encourages experimentation. You might start out wanting to build an alarm, but then you see a motion sensor in the kit and think, hey, I could make the lights in the workshop turn on automatically when I walk in.
And I suppose he should also find a good pinout diagram for his specific boards. I know the Raspberry Pi has a very standard 40-pin layout that has stayed mostly the same for a decade, but what about the Orange Pi?
That is a very important point. While many Orange Pi models try to mimic the Raspberry Pi pinout to be compatible with existing accessories, they are not always identical. You should always double-check the specific pinout for your exact model and version. A revision change from one year to the next can sometimes swap a couple of pins around. There is a website called pinout.xyz which is fantastic for Raspberry Pis, but for Orange Pis you usually have to dig into the manufacturer's wiki or the datasheet for the board.
That sounds like a bit of a treasure hunt, but I guess that is part of the fun of working with these more niche boards. They often offer better specs for the price, like the Orange Pi 5 having that powerful Rockchip processor. But you pay for it with a bit more work on the documentation side.
Exactly. It is the classic trade-off. The Raspberry Pi has the biggest community, the best forums, and the most polished documentation. If you have a problem with a Pi, someone else solved it 5 years ago. The Orange Pi often gives you more raw power, more RAM, or features like built-in M2 SSD slots, but you might be the first person trying to use a specific sensor with a specific kernel version. If Daniel is doing heavy audio processing or running a complex dashboard, that extra power is definitely worth the extra 10 minutes of looking up a datasheet.
I'm curious about the second-order effects of this. When you start adding all these components, screens, sensors, relays to a single board, do you run into issues with power? Can a standard USB power supply handle a Pi Plus, all that extra hardware?
That is a very sharp question, Corn. Power management is the #1 reason DIY projects fail or become unstable. People often see their Pi rebooting randomly or their Wi-Fi dropping out and they think it is a software bug, but it is almost always a voltage drop. Each GPIO pin can only provide a few milliamps of current. If you try to power a large touchscreen or a bunch of bright LEDs directly from the Pi's 3.3 volt rail, you will overwhelm the board's internal voltage regulator.
So what is the solution? Do you need a separate power supply for the components?
Often, yes. For a serious project, you use the Pi to send the control signals, the brains, but you have a separate power source for the heavy lifting, the brawn. You connect the grounds of the two power supplies together so they have a common reference point, but the actual juice for the motors or the bright lights comes from a dedicated power supply. This also protects the Pi. If something shorts out in your sensor array, you might blow a $5 power adapter instead of your $100 Orange Pi.
That seems like a very wise precaution. It's like having a fuse box for your project.
Exactly. And speaking of protection, another thing most people miss is something called a flyback diode. If you are using a GPIO pin to trigger a relay or a small motor, when you turn that motor off, the collapsing magnetic field can actually kick back a burst of high voltage electricity into the Pi. It is called inductive kickback. A simple 1-cent diode placed in the circuit can prevent that from frying your board. It is these little details, common grounds, flyback diodes, and decoupling capacitors that separate a hobbyist project that works for an hour from a home automation system you can rely on for years.
This is where your expertise really shines, Herman. It is easy to find a tutorial to blink an LED, but understanding the electrical engineering behind it is what makes the system robust.
I appreciate that. I just hate seeing people get discouraged because they accidentally damage their hardware. These boards are incredibly resilient in some ways, but they are also precision instruments. If you treat them with a bit of respect for the physics involved, they will do amazing things for you.
We have covered the basics of GPIO, the importance of the pinout, the utility of breadboards, and some project ideas. I want to touch on one more thing Daniel asked about, which was the multi-room audio. He is using USB speakers now, which is great. But could he use those GPIO pins for audio too?
He could, and this is a deep, wonderful rabbit hole. There are things called I2S DACs. I2S is another protocol similar to I2C, but specifically designed for transporting digital audio data. You can buy a small board, often called a hat, for the Raspberry Pi that sits right on top of the GPIO pins. It takes the digital audio data directly from the processor and converts it to very high-quality analog sound. This is how people build audiophile-grade streamers that rival systems costing thousands of dollars.
That is fascinating. So instead of a generic USB sound card, you are getting a direct digital path to a high-end converter.
Exactly. And because it is connected via GPIO, you have much lower latency and more direct control. Some of these boards even include built-in Class D amplifiers, so you just connect your passive speakers directly to the hat on top of the Pi. It makes for a very clean, integrated unit. For a multi-room setup, you could use software like Snapcast to sync the audio across every Pi in the house. You could have a Pi in every room, each with a high-quality DAC, all perfectly in sync.
It sounds like Daniel has a lot of exciting work ahead of him. From simple door sensors to high-end audio, those 40 little pins are really the key to everything.
They really are. And I hope he doesn't feel like he has to do it all at once. Start with the USB speakers, get the software running, then maybe add a single LED to show the system status, then maybe a physical button to skip a track. Build it up piece by piece. That is the most rewarding way to learn.
I agree. It is about that journey of discovery. And it is great that he is already using Home Assistant. That provides such a solid, unified foundation for all these different hardware pieces to talk to each other.
Definitely. Home Assistant is the glue. It doesn't care if a sensor is connected via USB, GPIO, Zigbee, or Wi-Fi. It just sees a sensor. That abstraction is what allows you to build such complex and powerful systems without losing your mind in the code.
Well, I think we have given Daniel a lot to chew on. I'm actually feeling inspired to go mess around with that old Raspberry Pi 4 we have in the drawer. Maybe I can finally get that automated herb garden project off the ground.
You have been talking about that since episode 300, Corn. It is finally time. I will help you with the moisture sensors. We can use an analog to digital converter, or ADC, since the Pi doesn't have native analog inputs on its GPIO pins.
See, there is always another layer. An analog to digital converter. I am guessing that is another I2C or SPI device.
You are catching on quick. Most sensors in the real world, like moisture or light, are analog. They provide a varying voltage, not just a simple high or low. Since the Pi is a purely digital machine, you need a little translator chip to turn that voltage into a number the Pi can understand. It is just another small, inexpensive component you can plug into your breadboard.
It never ends, does it? But that is why we love this stuff. There is always something new to learn, some new way to connect the digital and physical worlds.
Precisely. It is a hobby that grows with you. You start with a blinking light, and a year later you are designing your own circuit boards and automating your entire life.
Well, I think that is a great place to wrap up this part of the discussion. Daniel, good luck with the alarm panel and the audio setup. We want to see photos of the workshop once you have those breadboards glowing with LEDs.
Yes, definitely. And if you run into any weird electrical gremlins, you know where to find me. I probably have a datasheet on my desk right now about the exact issue you are facing.
I don't doubt it for a second. Before we go, I want to thank all of our listeners for sticking with us. We have been doing this for over 600 episodes now, and your curiosity is what keeps us going. If you've been enjoying my weird prompts, we would really appreciate it if you could leave us a quick review on your podcast app or on Spotify. It genuinely helps other people discover the show and join our little community of nerds.
It really does. We love hearing from you and seeing how you are using these ideas in your own projects. Whether you are a professional engineer or just someone who bought their first Raspberry Pi yesterday, there is a place for you here.
Absolutely. You can find all of our past episodes, plus our RSS feed and a contact form at myweirdprompts.com. We are also available on Spotify, of course.
Thanks for the great prompt, Daniel. It was fun to get back to the hardware basics.
It really was. All right, this has been my weird prompts. We will see you in the next one.
Until next time, keep experimenting.
Goodbye, everyone.
Hoppity.
This episode was generated using Gemini Flash 3. Text-to-speech engine was Chatterbox Turbo.
Thanks for listening to another episode of My Weird Prompts, an AI-generated podcast featuring Daniel Rosehill's AI prompts, as answered by a revolving cast of friendly AI characters including me, Cornelius the Sloth. Subscribe on Spotify or visit myweirdprompts.com.